Welcome to Maritime Intervention Updates. Today we have a very interesting lecture about obstacle avoidance in port environments, which is a subject related to waterborne transport, confined environments, and there's a lot of interesting technical background to be discussed on this topic. We have our colleague here, Nico Zantop, who would like to address this topic and present to you some of the results and the current research being done on this topic. I would just kindly ask you to place your questions in the chat, or um, you can also voice your question at the end of the presentation. And that's it. Nico, please, you have the floor. Please go on with your presentation.
Thank you, Cosmin, for your introduction. So today I want to talk about obstacle avoidance in port environment, and I want to demonstrate it and talk about our small unmanned surface vehicle, SeaLion, and then I will guide you through from the sensor to the motor how this obstacle avoidance will work with our autonomous vessel. First of all, I want to start with the history where we started with this unmanned surface vehicle. So we started with CML 1.0. It was a research vessel we developed for the RoboVAS project, and we used it to deploy underwater remotely operated vehicles. And we also developed already a waypoint controller, but we are not taking or looking into the perception module of this ship. So we decided to build a bigger ship with that is much more capable and have a perception system like a LiDAR, and I will go into more detail. It's bigger and have more capabilities regarding computational power and also the sensors. Here are some vehicle facts about the ship. So it's 2.2 meters long, 1.5 meters width, and it can handle payloads up to 100 kilograms, and it's completely electrically driven. And when we look on the system architecture of the ship, it's a distributed system, so we have a lot of different PCs in different domains on the ship, and we use ROS to handle the communication between these computers. Right now, we're using ROS1 Noetic, and we are planning to switch to ROS2 in the future. We are currently working on the transition from ROS1 to ROS2, and we're also simulating the whole ship in a gazebo environment. So now I want to introduce the system architecture for the obstacle avoidance. In the button down, we see the sensors and actuators. That's the hardware of the ship, and we have the submodules: perception, planning, control, and localization. It's the split is like in a lot of other mobile robots, and I want to go into detail in each subcomponent now. First, I want to talk about the sensors we use at our ship. So right now, our ship is equipped with some different kind of sensors for localization, for the perception, and it's equipped with the LiDAR, like a Velodyne VLP60. It will record point cloud, and we also have an IMU and a GNSS. It's from Xsense, and we also use a DVL to estimate the velocity relative to the seafloor. And another aspect for the perception system is having a camera, and we use the Z2i camera. Now I want to talk about the localization. So with localization, we refer to estimating the position and the most of the time also the orientation of an object moving through the world. And to solve this problem, because in the real world the sensor signals are very noisy, it's necessary to have some kind of filters. And you can use different kind of filters, example, a Kalman filter, a particle filter, a histogram filter, or even optimized-based approaches. I use like popular algorithms like extended Kalman filter localization or Monte Carlo localization. When we now have the accurate position of the ship and also the sensor readings, we can go to the detection sub-component. And here I want to talk about how can we detect the obstacle using a LiDAR sensor. And the LiDAR sensor will give us a point cloud. And this point cloud needs to be first pre-processed, because the point cloud data there are a lot of points and you need to reduce the load for the system. And therefore we use a voxel grid filter to create like smaller sub-point clouds that will describe the environment. In the next step, after the pre-processing these point clouds, we use some clustering. Therefore, we use the Euclidean clustering algorithm. And you see on the right side like how it looked like. We have these bounding boxes around the object. The objects are defined as width, height, and length. And we are also calculating the center position regarding the position to SeaLion, relative to SeaLion. The next step in the process is use this information in the mapping when an obstacle occurs. So here you can see now the next phase, it's the planning phase or the mapping phase. In this picture, you see now occupancy grid around SeaLion, and its size is defined by the perception range of the LiDAR sensor. And imagine in the occupancy grid, now everything is blue, so the cells are not occupied. And imagine there is an obstacle, then we can calculate a probability that the cell is occupied. And I want to demonstrate now how it looks like. Now the yellow star indicates an obstacle that appears, and the LiDAR system, like I described before, will recognize the obstacle. And we also introduced some safety boundary around this obstacle. Now there are different possible. Now we can see here that the path is blocked by the obstacle, and we need to readjust the planning and readjust the trajectory. So there are a lot of different possible ways to create a new trajectory. And here you can see now there are a lot of possible ways. So we need some kind of optimization for creating the new trajectory. And here we can use a optimization algorithm that will find the best way according to some defined criteria, like, for example, an A-star search algorithm. The next step in the pipeline is using the information about the new trajectory and also knowing the environment to make the ship move like it should be. So we need some kind of control, because in the real world there are disturbances that will disturb the ship, and we need to compensate and also make the ship move along the trajectory. So we use the cascade control approach, like we see here. We have a trajectory tracking controller and we have a velocity controller. The trajectory tracking controller will correct the cross-track error, like you can see here, and the heading error. And the output will be a yaw rate for the ship. And then the velocity controller will correct the longitudinal velocity and the yaw rate, and the output will be the thruster commands for the right and left thruster. I want to add here that the ship will be steered with a differential thrust. So if you want to turn the ship, one motor will spin faster than the other. That's now the overview how our ship works and all the subcomponents from the sensor side to the localization to the perception and then the replanning of the trajectory to the control, and then we have the output through the actuators to the thrusters. That was my small introduction how on a higher level how our ship will use obstacle avoidance in port environments.
Thank you very much, Nico, for this very, very interesting presentation. It's really interesting to see how far the ships have come through the last years. Now, I would like to switch to the audience and ask whether there are some questions. I didn't see any in the comment section, but maybe some people would like to directly ask them. If that's the case, please well, unmute your microphone or raise your hand, however you prefer. And we'll wait for a few seconds for the first questions. Or maybe until somebody formulates their questions, maybe I will ask you one because I'm also interested in the subject. Um, what are the next steps in the development? Because I saw a lot of localization effort, process estimation, and planning. What's the next milestone for the research that's being
So
done?
the next milestones will be on one side on the perception side. So we will also want to add some fusion of IES data and also more like a prediction of the ship behavior and we'll add this information to the replanning that you also take into account how the object that you detect will move in the future. And also what we want to add is like more like a rule-based approach to maneuver around the obstacle.
So make it even more intelligent.
Yes.
Add the AI. Cool. Thank you very much. In the meantime, there's a question in the chat from Dennis Büchner. Um, it says, can you detect moving objects and also their direction? And by moving objects, he means the object that the AI detects um,
Yes.
with a lidar. So
Yes.
the
So
ones that lidar detects. Yep.
right now we have an approach that we can predict the motion with a simple predict the motion of the detected obstacle with a simple model, but we want to increase it and also combine a camera to also use the camera to classify the object and get more information about it. And we also want to fuse the stereo camera data to have some another input source, and we also want to add a radar. So at the end, we will combine multiple sensors, and then we will improve the accuracy of the prediction.
Okay. Thank you very much. I think that was the question. Are there any other questions from the audience? Let's see. So it seems not to be the case. Then, first of all, thank you very much, Nico, for this very techy, interesting presentation. And for the rest of the people in the chat, that are applauding you. We can also mention what will be the next subject, which is a bit different. It's about quantum computing, so it's a bit of a different subject than robotics, but nevertheless, in the distant future, it will be something um, that will go along together. So my colleague Sebastian Rupert will present you next week, or I guess the week after Christmas, maybe, the maritime routing through quantum computing. Um, you will receive information about this event and when this will take place on your email, and hope to see you in large numbers also for this presentation. Until next time, have a nice Christmas and Happy New Year. Goodbye.
Also from my side, have a nice Christmas and thank you for your time here and wish you all the best. See you next time. Bye.